on this. I've just made sure that I have not muted anybody. So if somebody could check the text box for me and or do voice so I can see if both of those are working for me.
Testing voice.
All right, great, thank you. All right, great. All right, so as always, Zoom chat is available. So I have it right up here on screen so I can see it. Or you can chime in. We rarely have over 50 people, and so chiming in for a quick question has been working really well. So I don't think you should avoid that. And then, of course, yesterday's lectures were posted yesterday before my computer crashed. That was good. So those are available to you as well. So what we're going to do today is we're going to first do our administration, and then we're going to finish up chapter 16, which is additional reactions on aldehydes and ketones. Okay, so for administration, of course, we'll have Zoom class today, tomorrow, and Thursday. Second half of Thursday is our group activity. Okay, and I've had it happen a couple times. If you are unable to make the group activity, go ahead and do it on your own and upload it. Okay, so I want you to, it's mainly to, you know, get you kind of a peer-to-peer talking to each other, kind of like the SI sessions. But if you can't make it, I don't want you to lose those points. So what you can do is you can actually do it yourself, and if it's in that same week, upload it before noon on Friday, and you'll get full credit for it. If you're going to make it up for like something that happened last week or something, email it directly to me. I don't want you to lose the points for not being, you know, able to schedule at that time, because I know work and other things and dogs and kids, you know, get in the way of things sometimes. But I really want you to do the exercise, because you're seeing how, you know, I think the exercises are designed to, you know, get you thinking about doing things one or two different ways. And so if you can do it in the group exercise, great. If you can't, please just go ahead and do it yourself and upload it or send it to me email-wise if it's past due. And we can make sure that you get those points for you. Okay, so we have Zoom class, of course, through this week. We have homework for 16 and 17, which will be due midnight on Thursday. After midnight on Thursday, you can review it. You can go back and use it as a reference tool. So how I'm asking questions, the way the questions are worded, the kind of reagents we're looking at specifically in those areas, those are all the things that we'll be looking for on our exam on Friday. Okay, our group project today, on Thursday, is going to involve making of carboxylic acids and carboxylic acid derivatives. So we actually are going to learn a couple ways in this chapter to make carboxylic acids. We can oxidize down aldehydes. We can oxidize down other things. For example, the benzylic ketones can be oxidized or reduced, and we can do a lot of different things with that. So we're going to do some kind of playing around with that, kind of doing a reaction circle on those and showing you all the different reactivities associated with those carboxylic acids and some of their derivatives. And then we'll get into more of those derivatives in the following chapter, chapter 18. Okay. Our exam is again at noon on Friday. I have changed the settings slightly, so you should not have as many troubles. Last Friday was a little stressful for some of you, and I apologize, but I think the settings are changed enough that it should be, you shouldn't get kicked out as much. And so hopefully that'll go ahead. The grades for last week's activity, homework, and the curved test average should be up on Canvas. It should be up on Canvas. Double check that to make sure that your grades are showing up there on Canvas. If they're not, go ahead and email me and we'll talk. Homework question 1. Nobody's asked about homework question 1 yet.
Mine says, what is the correct IUPAC name for the following compound, but there isn't a picture on it.
Okay, mine shows a picture. And it's week 3, right?
Yes, week 3, because I have for 16.2 there's a picture, but my 16.1 there isn't anything there.
Okay, edit without unassigning.
It's like that for me as well.
Okay, let me see if I can't try to get that to go again. Let me see. Thank you very much, because this happened during the exam. I actually had a couple pictures like this not work in the exam. So I'm going to try to upload a new picture right now, live. Save, save, and close. All right. Okay, can somebody check on question number 1 and see if there's a picture there? Refresh your screen, and then, because it's showing up on my side this time.
So I just refreshed it and I don't see anything, but I'm gonna try again.
I can confirm. I just refreshed and I don't see a picture there yet.
Okay, I will, let me call Top Hat and find out what that's about, because I show a picture on my side and I show all things all things saved. All right. Let me go ahead and after class, could somebody run through and make sure all of them have pictures? And if you don't have a picture, tell me which question it is, and I will ping Top Hat to see what, because that happened on our exam too. And so this is the second time it's happened, and so it's becoming a problem for me. So I really need to know that. All right. So thank you very much. Okay, so back to our class now. We're going to continue on with chapter 16, the aldehydes and ketones. Okay, so let me share my screen. And okay, so let's, okay, there, all right, it stopped getting blurry. Okay, so last time toward the end of the class, we were talking about the carbonyl and how it can actually react with nucleophiles. And the whole point of its reaction is the fact that it has that polar bond, partially positive carbon, partially negative oxygen, okay? And so therefore, in this case, we were actually protonating it with an acid or a Lewis acid and allowing it to react then with even weak nucleophiles. Remember, nucleophiles that don't have a full negative charge or only just have a lone pair tend to be weak nucleophiles. And one of those that we will use today is water. So, excuse me. So the idea here is that we can use acid or base to activate that carbonyl to have slightly more positive charge on it, so it'll react with even poor nucleophiles. And in the next case we'll be doing, it'll be water as our poor nucleophile. Okay, so all right, moving on up. So this is kind of where we stopped yesterday. We were talking about how the reactivity of aldehydes and ketones are different. And in almost all chemistry, reactivity is derived by 3 things, okay? Sterics is a big thing, okay? Remember that when we wanted to do substitution reactions, once you got to secondary and tertiary alkyl halides, sterics was the driving factor, and that drove the mechanism. Electronics is the next thing we're looking at. The more polar the bond is, the more likely it is to react. The less polar the bond is, the less likely it is to react. That's why that carbon-hydrogen bond really does very little chemistry. We can burn it and that's about it, you know, because it's almost a non-polar bond. It's only got an electronegativity difference of 0.4 units. And so it's a very non-polar bond, okay? And even in a carbon-carbon double bond, even though that has that double bond, it's a non-polar bond. So things just tend to add across the pi portion of the bond and don't touch the sigma portion of the bond, okay? So that's electronics. The last thing is energy, and we're looking at either storing energy, so you have a potential energy in there, or releasing energy. And that's seen in our energy diagrams to be whether it's endothermic, we're storing energy, or exothermic. So you can really look at all 3 of these as your driving forces for every reaction you do when you move forward, and you should be able to get a kind of a holistic view of how these reactions happen. Where's the energy flowing? What is the sterics? What's the electronics? What's the driving force? Okay, so That being said, let's talk about the addition of water to aldehydes and ketones, okay? So in the alkene chapter, we were able to add water across a double bond, and it gave us an OH on one side and a hydrogen on the other, okay? So in the case of adding water across both aldehydes and ketones, anything with a carbonyl like this, we are going to be doing the exact same thing. The electron-rich portion, the oxygen, is going to add to the carbon, which is electron poor, that partially positive, and the hydrogen is going to add to the oxygen side. So in the case of this reaction here, let me pull up red ink right here. So when we add water across here, we're going to put the OH of the O of the water, the oxygen of the water, onto the carbonyl, and the H of the water onto the oxygen here. So what this ends up doing, and we can do this with acid or base, and I'll show you both, is that we're creating a diol. So we have two alcohols on that same carbon. So it's a very now electron-rich carbon, but it creates what we call a geminal diol, okay? So we can drive this reaction to form this, but it's not very stable, and we can easily, by removing water, move it back to form the carbonyl compound, okay? So in the overall scheme of things, this actual hydrate like this is only really, sorry, I'm doing my screen up here, there we go, is only practical for mostly aldehydes, and especially aldehydes with electron withdrawing groups, because it's a kind of steric, there's a steric component there, and there's that electronic component there. And so that these hydrates typically only happen on things like formaldehyde and things that are aldehydes with electron withdrawing groups, okay? Other than that, they are really not very useful because they immediately go back to their carbonyl compounds. However, we can use this reaction to our advantage to make taking that carbonyl-like structure out of it so that we can react other places on the system, okay? So I want you to think about this as like starting to look at taking the carbonyl character away from our carbonyl temporarily, and then we can bring it back by shifting the equilibrium, okay? So the way I want to talk to you about this, so these are the hydrates right here that we just talked about. If we use an alcohol instead of water, we can get to what we call a Hemi Acetal or half acetal. Okay, so in the case of this, instead of adding water across there and generating two hydroxys on the same carbon, we end up doing where we add the oxygen of the alcohol to the carbonyl carbon, and then we transfer the hydrogen over to the carbonyl oxygen to give us this structure. And the structures are very commonly done where we have the two groups that are on our aldehyde or ketone. So one of those R's can be an H or it can be an alkyl group, okay? And we end up with this ether structure right here and our alcohol here. So if you have an ether and an alcohol on the same carbon, that's a Hemi Acetal, okay? So in general, they are not stable unless they form rings, okay? And that has a little bit to do with thermodynamics, but it makes, when we have it form a ring, it can be stable. You can isolate it. It doesn't necessarily react very quickly with water, okay? And the most common place we see this is when we take sugars like sucrose or glucose and we close the ring, they can form this semi-acetal structure. Notice that we have, this would be our R group of our alcohol, and this would be the point where the carbonyl was, because we have the OH here and an O with an R group on this side. So that's the site of this Hemi Acetal, okay? So these aren't really too stable, so we don't typically use Hemi Acetals when we're looking at these chemical reactions. We actually move on to something a little more stable than a Hemi Acetal, and that's called an acetal, okay? And I'll show you that structure in a minute, okay? So for the formation of that Hemi Acetal, it's basically an acid-base reaction that we're going to use, and then we're going to transfer a proton. So the first step in this, and again, you can make them with acid or base. The first thing we're going to do is acid. First step in every acid-based mechanism is the transfer of a proton. Okay, so the first thing we're going to do is we're going to transfer a proton from the, in this case, it can be water or an alcohol. Since we're making a Hemi Acetal and not a hydrate, we're going to use alcohol here. So the alcohol is protonated in the system and transfers that proton to our carbonyl, giving us a species where the oxygen right here, okay, great, is protonated. And when it does that, it means we have an equilibrium, a resonance structure where we can have that. This becomes a lot more positive now because we have the ability of these electrons to kick out and reside on the oxygen, making that carbon a lot more positive. And let me, and when we do that, what happens is now our neutral nucleophile, the lone pairs on that oxygen of the alcohol can act as a weak nucleophile. And because we have more positive charge on this carbon now, these electrons can come in and create our new sigma bond, okay? When we create that new sigma bond right here, so because that alcohol still has that hydrogen on there, it's a protonated alcohol species. And then we can use either an alcohol or water in solution to act as a base and get to our neutral species, okay? So when we do that, we end up with our Hemi Acetal, and we've regenerated our acid species here, okay? Notice every single step of this is in equilibrium, meaning if you add more water to it, it's going to go back to the hydrate or going back to the carbonyl compound. Okay, so every single step in this is reversible. And typically you use this as a driving force to remove water, or at the end of the reaction, you have a large amount of the alcohol there so that it can drive the reaction toward this Hemi Acetal structure. Again, the R and the alcohol, the ether and the alcohol are the determining factors to make you an Hemi Acetal. Okay, so in the case of a base mediated system right here, what we've actually done is instead of having our alcohol as a poor nucleophile, we've actually deprotonated that alcohol and made it a good nucleophile. So we don't have to protonate that oxygen to make the carbon more positive. We now have a negative charge on oxygen. Those electrons can reach out and form that new sigma bond with that carbonyl carbon, and then we have the charge residing on that carbonyl oxygen. Now that carbonyl oxygen is now a stronger base and will deprotonate the solvent or some of the alcohol in the solution and give you your protonated Hemi Acetal, plus regenerate your base. Okay, so the difference here is that you already had a negative charge on your nucleophile, and your nucleophile just reacted directly as a nucleophile to do that in that tetrahedral. And in most cases, when we did this before, those were an intermediate state, a tetrahedral addition state. Here it is our final product, our Hemi Acetal. Okay, so if we have an ether and an OH on there, that is a Hemi Acetal or a half acetal. So what we want to do is, well, if instead of having that hydroxy on there, we actually had two of these OR groups on there, that is a different structure, and these tend to be more stable. And these structures are called acetals, okay? So when we go to the next slide here, okay? So technically, because we have two oxygens on the same carbon, and this does not have the same reactivity as a standard ether, we actually don't call them ether. It is a special group. It is called the acetal group. And because it is very susceptible to acid, it's very susceptible to base, it does not react like an ether, therefore it is not an ether. Okay, so in the case of formation of the acetal, you have to have two equivalents of your base, of your alcohol, and then either acid or base. Typically acid's used because it's a lot easier to do. And so you would take an aldehyde or a ketone plus 2 equivalents of an alcohol, and then to drive the reaction to completion, to keep it in this acetal state, we tend to remove water from the reaction. Okay, so again, if we added water, it's going to drive the equilibrium back the other direction. So to make these, we remove water from the solution and generate those 2 carbon-oxygen-carbon bonds on that same carbon, the carbonyl carbon. Okay, now, when they are these straight chains, they're not as stable as they could be. However, if you make a cyclic version by having a diol, these are incredibly useful synthetically, okay? They are very stable to reactions with like LAH and sodium borohydride, and so that you can actually remove this reactive ketone from a reaction by making it into your acetal, okay? So this is probably the most common way to use an acetal, is to take an aldehyde or a ketone and then take this diol, 1,2-ethylene glycol, ethane diol, or ethylene glycol, as the other name says. And you typically use an acid that dissolves in an organic solvent, okay? And we use an acid that dissolves in an organic solvent because we want to remove water from the reaction as we go, okay? So if we do that, and if we remove water, we're gonna drive the reaction to this, where is my, there. We're gonna drive the reaction to this acetal, and by removing water, we can trap it in that cyclic acetal system, okay? So let's look at how we make this, what the mechanism is of making this, and we'll look into a couple different acids we would use. Okay, so the first thing that happens is we react that first equivalent of alcohol to make the semi-acetal, the Hemi Acetal. The Hemi Acetal forms first, and then at that point, the second equivalent of the acidic alcohol can come in and protonate the OH group, okay? If it protonated the OR group, and then it would just go back to starting material. So, well, that reaction is reversible. To drive the reaction forward, if we protonate the OH group on that former carbonyl carbon, we can actually then eliminate water by having the electrons come down from the RO here, and then that would kick out neutral water, generating this intermediate species here, okay? Notice we're using an aldehyde here, and then we generate water from that. So that's the first equivalent of water we've generated here, okay? So notice this looks a lot like that first step of forming the Hemi Acetal, where we protonated the oxygen and we had that positive charge on oxygen, okay? So that activates that carbon, it makes it more electropositive, so that now we can have the neutral alcohol species come in and make the second oxygen carbon bond, shown here. And now our alcohol in our reaction can act as a base and deprotonate that, liberating our neutral species plus regenerating our acid. Notice this is the acid, the protonated alcohol we used up here in the beginning. We regenerate that at the end. Okay, so it starts off like the Hemi Acetal. We have that OH there. Remember, OH is a kind of bad leaving group because you have that hard negative charge. So we typically remove OH by protonating it and having it leave as neutral water. Once it leaves as neutral water, we can then have attack by alcohol. So see where having a large concentration of that alcohol would help drive the reaction, because the reversed reactions will get fewer and fewer, and the forward reactions will get more and more. And so we can drive it to this full acetal. Okay. Okay, so the whole reason we talk about acetals is we like to use them as protecting groups. Remember, in the last chapter, we introduced a protecting group where we took the acidic proton off of alcohols with a silicon group. And we only did that because we couldn't react Grignard reagents and other things with these protonated species. So we were able to decrease the reactivity of that acidic proton and then regenerate it at the end of the reaction. In the case of acetals, what we want to do is decrease the activity of a carbonyl compound, specifically so we can do some kind of nucleophilic attack or reduction on a different species. Okay. In this example here, what we want to do is we want to selectively reduce one group or the other. And in this compound here, we have a ketone on one side and we have an ester on the other. Okay, so if we wanted to selectively reduce down that ketone, all we do is add sodium borohydride, because sodium borohydride doesn't reduce down esters. Okay, however, if we wanted to selectively reduce down our ester, the ketone would react first if we added a lithium aluminum hydride. So what we have to do is take out the carbonyl character of that carbonyl temporarily and then regenerate it at the end. Okay. So if we wanted to selectively reduce down the ester, we would have to protect that carbonyl carbon. Okay. So and the way we do that is we would use an acetal. Specifically, most of the time we're going to see it used in synthetics is going to be in a cyclic acetal. All right, so with all protection, deprotection processes, there are 3 steps. We have to protect the functional group we don't want to react. We have to carry out the desired reaction we do on the other functional group. And then we have to remove that protecting group to regenerate our original functional group. Okay, so in the case of this example where we're using an acetal to protect the ketone, what we're going to do is we're going to use that cyclic acetal, and in this case we use ethylene glycol right here. Okay, so it's a nice simple diol, and then when we react that with our ketone, we get this nice 5-membered ring right here. Okay, now it's not an ether, however, it does take out all of the partially positive charge on that carbonyl carbon, and therefore it does not react with other things that would normally attack carbonyls. Okay, so in the case here, we're using an acid, and it's called tosic acid. Okay, I'm going to draw that for you. It's toluene sulfonic acid. So we have a toluene and we have a OH here. This is really commonly used. It's TSO, and so this part right here is what we would call the TS portion, and then OH. The reason this acid is used is, number one, it's a fairly strong acid. Number two, it's also soluble in most organic solvents. And remember, we want to drive the reaction by removing water from the system. Therefore, we want to do it in an organic solvent in the absence of water. So a lot of our acids, our strong acids in particular, are only soluble in aqueous solutions. So we are using this different acid to do our catalysis. Okay, so once we have our alcohol and our tosic acid, we remove our water, we get our acetal here. Our acetal will not react with reducing agents that attack carbonyls. Remember, our lithium aluminum hydride and our sodium borohydride only attack carbonyls, but sodium borohydride is not strong enough to attack esters, but lithium aluminum hydride is, and it takes esters all the way down to primary alcohols. So we're going to take our ester down to a primary alcohol using our lithium aluminum hydride. And then of course the second step is adding water to decompose that aluminum complex that it makes. And then just by adding water and some more acid, we can clip off our acetal and regain our carbonyl compound. Okay. So we're using that acetal to take the carbonyl character out of a functional group. Notice we do not form acetals with esters, only aldehydes and ketones. And they form faster on aldehydes because of the sterics and the electronics we talked about yesterday. All right, questions on that? Okay, so the whole point of an acetal is we're using ethylene glycol and typically tosic acid to make something not have carbonyl character so we can react to some other carbonyl in our system. And of course, works great with this particular type of step where we're reducing down esters. Okay, so there are some different kinds of acetals, and we choose the different acetals because of the product we want to end up with. So in the formation of this acetal, we generate our ketone just by adding water and acid, okay? Okay, we have another derivative of that, we call those thioacetals. So instead of using a diol, where we have two alcohols at the end of things, we actually use a dithiol, okay? So we're replacing sulfur, we're replacing the oxygen with sulfur, and that creates a different bond. That creates because the sulfurs are much bigger, are much fluffier, we can actually do a different reaction in the end to remove it, okay? So let's look at that reaction. So basically all we're doing is replacing the oxygens on the ends with sulfur, and we're using a different catalyst. We actually can use a Lewis acid catalyst. We don't have to use a straight proton acid. So we have boron trifluoride here, and that creates our cyclic disulfur compound here and eliminates water as well, okay? Again, it only forms on aldehydes and ketones. So when we form it on aldehydes and ketones, it does not touch esters or carboxylic acids. Okay. Now, the great thing about thioacetals is instead of just adding water and getting it back to the carbonyl compound, it actually does a great job of, you can reduce it off with hydrogen and a catalyst called Raney nickel. And what that means is both of those sulfols will be removed and you can put two hydrogens there. So you can take your carbonyl all the way down to a CH2 after you've protected it. Okay, so this is really good when you want to do a selective where you don't want an alcohol ending up there, or you don't want an addition product with your aldehyde or ketone, but you eventually do want a CH2 group. And I'll show you how to use that on the next slide. So the general concept would be that we would be able to take off both of these sulfurs here and add two hydrogens to the methyl group, and then we of course regenerate this right here. So the key here is hydrogen and Raney nickel. Okay. So that's another way to protect a carbonyl group, okay? We talked about the hydrate would protect a carbonyl group. We had the Hemi Acetal that can protect the group. We have the acetal, more importantly, the cyclic acetals right here. We have the thioacetal, and we can either regenerate the carbonyl or generate a CH2, okay? There's another way to protect the carbonyl, taking out that carbonyl-like structure where it's the partially positive carbon and partially negative oxygen, and that is by changing the electronegativity of the atom bonded to carbon. And we do that with nitrogen. The nitrogen-carbon bond is less polar than the nitrogen-oxygen bond, and therefore it would decrease the reactivity at that carbonyl carbon. Okay, so the way we do that is we react our ketone or aldehyde with an amine, which is a stronger base than the water that it produces. Okay, so, okay. All right, so the generalized structure of the amine is the fact that we are going to take two hydrogens off of the nitrogen and the oxygen off the carbonyl and remove water. Okay, but we just have to do it in a stepwise fashion. And again, the whole reason it drives there is that our amine is a stronger base than the water we generate. Therefore, it's all about having the weaker base be removed from the system. Okay. It is a reversible system. If you add a little acid and water, you can drive it back the other way. Okay. So as with all of these, what we've done with the hydrate, we had a neutral water acting as a weak nucleophile. And that's the first step in the formation of an amine. Okay, so when you have an amine with 2 hydrogens on it, so it's a primary amine, and we'll talk about that more in chapter 20, it can react as a Lewis base, so attacking the carbonyl here, generating our polar intermediate here. Okay, so we have a positive charge on nitrogen and a negative charge on oxygen. So the best thing for us to do is to try to make a neutral species, and we do that by transferring a proton from the nitrogen to the oxygen to give us our neutral amino alcohol compound. Just like our hydrates, it could be more stable. We could have another reaction there. And so in the case of our amino alcohol here, we protonate the water here, the OH here, to generate our protonated species that then leaves as neutral water. And when it does that, our electrons from our nitrogen kick in and form our double bond with our carbon, giving us our initial protonated species, the iminium ion. And then the water will act as a base and deprotonate it, giving us a neutral imine. Okay, so the structural part of an imine is you have a carbon double bonded to a nitrogen, and then there's something else bonded to that nitrogen. It's either going to be a hydrogen or an R group. Okay, because remember, nitrogen needs 3 bonds. Okay, so now, and again, the driving force for this is that the water leaving is a weaker base than the amine you're starting with. Okay. Okay, so there are a bunch of different structural analogs we can have on this. We can have the R group be hydrogen, and that would be a simple amine with ammonia. Okay. Now, if we have just a primary amine, which are sometimes easier to use, you're going to end up with what we call an imine, I-M-I-N-E, okay? And so it's going to have the general structure of this right here. And notice that because there's no free rotation around that carbon-nitrogen double bond, we do have E and Z isomers possible, okay? It's going to form in equal amounts when you form it. It just depends on which side the hydrogen's coming off on when it forms. So you're going to form a mixture of the E and Z isomers there. However, if you don't have a hydrogen or a carbon on there, we can actually have other groups there, oxygen, nitrogen, or even other groups, and that will change the actual name of the compound. So in the case of, if we replace that hydrogen or that carbon group right here with an OH group, this is what we call an oxime, okay? It's basically giving us the same functionality. The nitrogen is more basic than the oxygen, and therefore it bonds and gives us that carbon-nitrogen double bond, but it's another structural analog that we can use to protect or react our carbonyl compound. Okay. This is used a lot in the presence of aldehydes, in particular because these are really, really water soluble. Okay. Now, another derivative is we can take, instead of having that R group or that hydrogen on there, we can actually have an amine there by reacting with a dinitrogen compound called hydrazine, okay? Now, hydrazine, also used as jet fuel, but it's also pretty toxic, so we like to use it in little amounts when we do use it. But when we do that, we end up with an amine hanging off that nitrogen, and we have a different compound known as a hydrozone, okay? Hydrozone. In fact, this is commonly used in the organic teaching lab to show whether or not you have a ketone or not, because when the phenylhydrazine compound here reacts with ketones, it creates highly colored compounds, okay? So when we form these hydrozones, it can be the E or the Z, it's a mixture of both, because of just which side the hydrogen comes off when it forms the double bond. Okay. So the only difference here is that we still have 2 nitrogens right here. But then instead of having a hydrogen on this nitrogen, we actually have an R group on here. In this particular one, we have a phenyl ring, and these create very highly colored species, okay? Here's another example right here, all drawn out. Again, we have to have those two nitrogens. One nitrogen loses water, forms that double bond with the carbonyl. The other nitrogen is bonded to the nitrogen and two other things, in this case, a hydrogen and a phenyl ring. And these are also used as kind of a qualitative test to figure out whether you have an aldehyde or a ketone on a substrate. Okay, so that's if you have primary amines or amines with available, two hydrogens available so you can actually dehydrate. Okay, so notice all of these have two hydrogens on the nitrogen group here that can be used to remove the oxygen from the carbonyl compound. So those are the two hydrogens in the water leaving, and the oxygen is from the carbonyl. What if you don't have that second hydrogen? Okay, if you don't have that second hydrogen, you can still do the original nucleophilic addition, but it creates a slightly different product. Okay, so I'll pull this up. Okay, so in the case of having a secondary amine, you can only remove one hydrogen from that nitrogen to make that double bond. You cannot form the nitrogen carbon double bond. However, if there's an alpha hydrogen, if there's a hydrogen next to that carbonyl, come on. There it is. All right. If there's a hydrogen next to the carbonyl here, we can actually form a double bond next to that bonded nitrogen here. So if you think about it, it's very similar to the amine derivatives that we have up here. However, the double bond is now between two carbons. And when we do reactions, we can do reactions specifically on carbonyl compounds because we have a carbon-carbon double bond. Okay. So let's talk a little bit more about that amine derivative, the enamine derivative here. Okay, so the only difference was we had two hydrogens on all of the nitrogen species above. Here we only have one. So we can't lose water and create a carbon-nitrogen double bond. So we have to create a double bond somewhere. And where we do that is that next position over from the carbonyl. Okay. So just like in all of these species we had before, the first step is our amine reacting as a poor nucleophile, okay? So our amine is reacting as a poor nucleophile and coming in and attacking our carbonyl carbon to give us this new species right here. In this case, we have generated our new carbon-nitrogen bond, and we have a charged oxygen here. Of course, we want to protonate that charged oxygen. So we're going to transfer the hydrogen from the nitrogen over to that oxygen, giving us our amine version of our Hemi Acetal. Okay, so this is a amine version of the Hemi Acetal. Okay, but again, we cannot transfer another proton off of nitrogen because there's no proton to transfer to make that double bond. So what happens is we will protonate our alcohol, and when water leaves, right here, it forms a double bond with the carbon. It'll form a double bond with the carbon next to it eventually. Okay, so when this water leaves right here, the electrons from the nitrogen kick in to form a double bond with the carbon. But notice this is a charged species. We have 4 bonds to nitrogen and we have a positive charge on nitrogen here. Okay, so this is not very stable. So what happens is one of the protons, let me blow this up, from the adjacent carbon can now be removed. And those electrons can kick in, and that kicks out the double bonded electrons to give us our neutral nitrogen species. Okay. So the whole point is that we had to remove a hydrogen to generate our neutral compound in the end. We still have a double bond, but instead of between the carbon and the nitrogen, we now have it between two carbons adjacent to the nitrogen. Notice the nitrogen is still bonded to the carbon with the carbonyl, and there's still a double bond to the carbon with the carbonyl. It's just, it's now double bonded to a carbon and not a heteroatom like oxygen or nitrogen. Okay. And again, the whole reason to use these is, number one, they will decrease the reactivity at that carbonyl site, and we can use them as a qualitative test to show if we have that derivative. There's also a lot of biologically active species that use all of these different functional groups in various ways to make them water soluble and react a certain way. So there's a lot of these found in biomaterials and biochemistry. Okay, so that brings us right to about 12:45, okay? I have one more set of reactions to talk about, but what I want to do is I want to take a break here and answer any questions about the formation of these protected aldehydes and ketones by the formation of the hydrate, Hemi Acetal, Acetal, Thioacetal, or any of these nitrogen derivatives. Okay, I'm going to stop recording and then let you speak freely.